My name is Grace Akot from RCMRD, Regional Center for Mapping of Resources for Development. And it's been a pleasure moderating this webinar together with my colleague Sonia from European Space. This event is organized under Genius and Africa program at RCMRD, which is an initiative of African Union, Commission, and supported by European Union. We've been ordered to collaborate with our partners from European Commission and European Space, whose contributions have made this webinar possible. Over the 2 days we've had the webinar, we've had insightful sessions on Copernicus program overview and its thematic services. On the second day, we did use cases of Copernicus in land degradation, monitoring, agriculture, and food security. And today we'll be focusing more on the practical side of things, on how to access and use Copernicus data for your analysis and applications. We are honored to have two speakers guiding us through today's session, and Sonia will be introducing them in a few. And as always, you can always post your questions on the Q&A during the session, which will be addressed after the presentations in the Q&A segment. As we proceed, I would like to kindly request that all participants take a few minutes to fill out the short feedback form that I'll be sharing in the chat. And we appreciate to know what you've gained from the webinar and any other recommendations you might have for us for future improvement of the webinars. I hope today you have a very hands-on session and you are inspired to use Copernicus more in your work. Over to you, Sonia.
Thank you, Grace. Pleasure to be here on the third day. So as you said, that during the first 2 days, we heard a general overview of Copernicus and the services, and you have seen a lot of beautiful satellite images. So today we have with us Andras Zelinsky, community evangelist at Synergize, Pratisha Sharma, geomatics engineers at Vito Remote Sensing, and Jeroen Dries, software engineer at Vito Remote Sensing, that will explain to us how we can produce the images and how we can access the data. So I leave the floor to Andras for his presentation on the Copernicus data space ecosystem and demonstration of the Copernicus browser. Thank you.
Hello, everybody. I will present a quick overview of Copernicus data space ecosystem and its functionality, and then we will do a hands-on using Copernicus browser and moving over to the CDSC Jupyter Lab. So after understanding the general structure of the ecosystem, I hope that you can all get engaged in working with the data. For the hands-on part, I will be sharing links to the scenes I show in the meeting chat. So if you can't follow the exact place where I am, I will be sharing a link, and if you click on that, then it should open up the same place in Copernicus browser. I will also be sharing the links to the Jupyter notebooks that I am demonstrating. So Copernicus data space ecosystem, well, this is the data gateway and cloud platform for the Copernicus program. And I'm sure you've heard a lot about the Copernicus program. Just a quick overview. We have a complementary scheme of Earth observation satellites focusing on environmental monitoring. And in the Copernicus program, we have a long-term commitment to sustaining this fleet and to sustaining the ground infrastructure and services, which enable the functioning of this system, this infrastructure. So we have synthetic aperture radar for mapping under all weather and lighting conditions, looking at vegetation structure, looking at terrain movement. We have Sentinel-2, which is mainly optimized for vegetation mapping, for agriculture, and for forestry conservation, disaster monitoring. We have Sentinel-3, optimized for oceanic applications for water quality monitoring, but also collecting thermal imagery. We have Sentinel-5P, which looks at atmospheric pollutants. Sentinel-4 and Sentinel-5 are also going to be atmospheric satellites, but they haven't been launched yet. And Sentinel-6 is another ocean topography satellite looking at the water surface of the oceans. So we have this fleet. We have all the data coming in. It's actually several terabytes a day. But the big question is how to put this into practice. How can we actually design operational applications that solve real-world problems based on satellite data? And one of the most important, actually the most widespread civilian application of Earth observation worldwide is definitely agriculture monitoring. And among this, the European Union Common Agricultural Policy monitoring stands out as a large-scale operational system. So what we do here is the farmers, they inform the government about the farming practices they are doing. They are eligible for a subsidy, so they get money for farming in the correct way. But we have to check whether they are doing what they say. And this is done 100% by satellite imagery at the first stage, and field monitoring comes afterwards only for the uncertain cases. So what you see here is a map of Slovenia divided into hexagons. And a hexagon is green when most of the parcels have been checked and the check has been successful. And a hexagon is going to be yellow if the parcels have been checked, but we are not sure what we see. We are not sure whether the farmers are doing the right thing. And as the season progresses from April, May, June, all the way to December, we are collecting more and more images. We are gaining more and more information on the farming practices. And this way, the number of yellow hexagons is slowly decreasing and more hexagons are moving to green. So what this means is just that as the year progresses, as we collect more and more information, we are able to verify the farming practices in Slovenia. We can pay the subsidies to farmers, and we only have a very limited amount of field checks to do. This is an application where we have a very clear demand. We have a set of regulations to check. We have a processing chain, including crop classification, including monitoring the timing of certain practices. And this is what we use based on satellite imagery. So all this is based on Copernicus Data Space Ecosystem, which is the data platform. If you take a typical data processing pipeline, it starts with data access. The satellite takes the picture, it collects the imagery. This has to be sent down to Earth and stored in some sort of a server, some sort of a repository. And then in the next step, when you initiate a processing task, you will select a subset of the data. You will filter it, remove the cloudy images, remove the images you don't want to use. You apply some sort of a calculation. Right here, actually, this is Stromboli volcano, and we are applying a visualization script which highlights the warm or hot lava emitted from the volcano. And then you create some sort of an output. In this case, it's a GIF. And so all this processing has to take place somewhere. And the end result is a visualization, like a graphic, some sort of a summary of the quantitative information in the process, and that is visualized on your computer. Now, the big step forward in Copernicus Data Space Ecosystem is that all of this takes place in the cloud. So the data access part, obviously, with the servers, but the processing is not done on your server, your computer. You don't download the data. You just send the commands over to the cloud where it's actually carried out. And even the statistical analysis or the visualization rendering is done on the cloud. And the only thing that is sent to your computer is the actual image that appears on your screen. So this means that with Copernicus Data Space Ecosystem, the performance of your computer is not a limitation anymore, because everything that happens is done in the cloud. The little arrows that connect these stages, this is the data infrastructure. And a good data infrastructure is sort of invisible. It works in the background. It helps you do your thing without demanding too much attention. This is what we aim for with CDSE. Copernicus Data Space Ecosystem is composed of many different components, different tools, and these work together to produce this infrastructure, this ecosystem that allows you to work with the data. Of course, the core of everything is Sentinel data. And here again, we have a step forward compared to the Copernicus Open Science Hub, which used to allow immediate access to the data from the last 2 years. Now you have all the Sentinel archive starting from 2014 immediately accessible. You don't have to wait for a rolling archive to be processed. And you can access the data with APIs. Now, APIs, and I'm going to talk about this a bit more in the next slide, APIs are application programming interfaces. So these are machine-to-machine interfaces that allow your code to communicate with our server in a standardized language. And this means that you can send commands. You can actually access the data collections in your code the same way as you would if you define a variable. If in your code you say x equals 4, then next time you call x, the computer knows that the value of x is 4. And you can do the very same thing with a satellite data collection. You can say the Sentinel-2 image of Berlin from the day of yesterday with the cloud filter and treat this as a variable in your code, which allows you to directly work with it. And so these APIs enable Copernicus browser, which we will test in quite some detail. This is an online interface to satellite imagery. In the background, it works with the APIs because we are requesting the imagery from the server that you are viewing, and we are applying calculations and visualization algorithms that also run in the API. We also have additional datasets, Copernicus contributing missions data, so higher resolution datasets for some applications, additional Earth observation data such as terrain models. All this comes together to enable you to develop Earth observation services with a sort of a complementary set of data. And now the other big component is cloud computing capacity. Again, computing capacity is expensive, it's complicated. You have to create a virtual machine on a server, or you have to set up a processing station at your university or your company. And the Commission and ESA decided to provide a considerable cloud computing capacity for free. So this cloud computing capacity is on the very same machines which do the data storage. And this means that the data is stored very close to where it's processed. So the cloud computing capacity is not just there, it's also super fast. So it's possible to give commands using the APIs to these cloud computers, and it's going to run your commands in the cloud and give you the result. Another bottleneck in Earth observation is the availability of code. You will all know it's not very easy to learn EO coding. We have created a repository of various coding tools, Jupyter Notebooks, custom scripts, OpenEO, process graphs that allow you to go step by step into the world of EO coding to make this easier. And combining the cloud computing capacity and the code repositories, we have these online code labs like the Jupyter Lab in CDSE, which allow you to work directly with the data using these coding tools on cloud computing capacity provided by the infrastructure. And finally, over here, we have federation services. Not all the data is hosted in CDSE, but it's possible to federate with a different repository to access data from other repositories and to process them together with Sentinel data on the Copernicus data space ecosystem infrastructure, because we are accepting their identity services and they are accepting ours. So all this put together forms an open ecosystem. It's ready for innovation. It's there for data providers, for solution providers, and we hope that it's going to contribute to growing the industry. A little bit more about downloading versus API access. The old way we used to access Earth observation data, I am sure a lot of you remember sitting in front of the computer and waiting for the data to download. And this is because data is large. We have to compress it if we want to move it through the network. And if we compress it, we are creating a predefined scheme of tiles, of boxes, and you have to decide which tile you want to download. You pull it down, and then you unzip, uncompress it on your computer. Again, since the data is in chunks, in tiles, a lot of it is on the tape archive. You have to submit a query. You have to wait for it to be made available. And then once you download the data, you are storing it on your site, on your computer. Again, one of the things we all remember from Earth observation is having a massive stack of hard drives or a NAS or something that stores all the data we use. And then when you select the subset of your data after unzipping the tile, you move it to a server or a virtual machine, you process it there. And all this requires a lot of money. If you want to work with a lot of data, you have to invest a lot of money on a big server, a lot of storage space, a lot of memory. And if you want to grow, this is very difficult to scale up because first you have to spend money and only then will you be able to generate income. So this is the problem we want to solve with API access. Down in the engine room, the solution is actually an uncompressed data format. It's called the Cloud Optimized GeoTIFF. It allows you to create a subset of the data without actually opening up the full file and loading all the file to the memory. So this is an uncompressed format. And this way, you can select the exact area of interest where you want the data, and you can query only that from the server. And again, if you know the operation you want to do, you don't have to download it. You can run that operation straight on the server and only download the results. And so this means you're not storing raw data on your site. You're not moving raw data through the internet. You're only moving the data products through the internet. And this makes it, again, a lot faster. Processing takes some capacity, but this is done on machines that already have the data on board. You get the virtual machine defined that accesses the data collections. And this means you don't have to invest all that money, because you can start developing code, you can start developing a solution using the free capacity. And then if you need more, because you're moving to a larger area, you can buy more quota, you can scale dynamically without having to wait for a server to be delivered to your office. Copernicus Browser is our sort of intro level tool. It allows you to search and query and download the data products. This also works in the tile scheme, but it can also work for a small area of interest. It's a visualization and analysis tool, so you can open it up in a web browser, you can move the imagery around, you can look at different visualizations, you can calculate things in a time series, and we're going to explore that in a moment. You can export print quality images, you can create time lapses, you can analyze changes that happen in areas, and it also works in 3 dimensions. You can create very pretty images. But I think the most important development tool is actually the Jupyter Lab. Again, if you have already experimented with Earth observation code development, or if you're regularly coding, you know that you have to maintain a coding environment. So you have to keep the libraries up to date that you use. You have to select which infrastructure to invest your time in, what tools to learn, what to install on your computer. And all this takes a lot of time. Now, the Jupyter Lab is an onboard server where the dependencies are already installed. The APIs are already there, and it has direct access to the data collections. And this works using the structure of Jupyter, which is a combination of Markdown, so formatted human-readable text code in blocks, and images or maps. And the images will display the results of your code, and this allows you to experiment step by step, looking at the results directly as you work through the notebook. We have some tutorial notebooks which are at introductory level. I'm going to show a couple, but we also have full-scale end-to-end processing examples for a wide range of use cases. We have OpenEO, and I don't want to talk too much about OpenEO because my colleagues are a lot more proficient, but this is a code-agnostic API, so it's not dependent on a single coding language. It's also compatible with many different data backends, and this means that you can really use it as a glue to put together a pipeline from different blocks, different modules, different data sources, and then scale the whole thing up. It's also optimized for good sharing of the algorithms of the product. So again, portability is one of the big problems of Earth observation. I develop a pipeline somewhere. Can I run it on a different computer, a different area of interest? Well, with OpenEO, all this is not just possible, but actually easy. And then we have the commercial element of CDSC. CryoDS is a virtual machine provider. Again, these virtual machines directly access the data repository of Copernicus Data Space Ecosystem, and they run the very same APIs that you can learn using the free tools. So if you develop a pipeline using the free quota, but you need to run it on a very large area, you want to use it for a commercial purpose, then you can take the whole thing to CryoDS and grow it as your application grows. So for all these tools, of course, we need your contributions. This is like a set of building blocks, or like a set of tools in your garage. You can contribute data sets, you can contribute code, you can contribute use cases, and we hope that this large open scheme of publicly accessible data sets and tools is a platform for collaboration, because it's a standard ready way for many people to work with the data. All in all, I think that CDSC is a transformative solution. Under transformative, we mean that it's larger than the sum of its parts. It has more impact than the individual incremental changes that are included in it, because we are making data sharing easy, we are making collaboration easy, we are breaking the boundaries of big data by providing online infrastructure. We really hope that a lot of people can enter the world of Earth observation and provide solutions. I will be ready for your questions after this time block. So please note them down or paste them in the Q&A, and then we can talk about them later. But now, first things first, I want to take you to the CDSC main page. So this is the Copernicus Data Space Ecosystem homepage. It has a roadmap for updates. It has a section on news and blog posts. It has a gallery where you can look at interesting examples of images. And this green button is where you register. If you click here, it takes you to Copernicus browser. This is the next thing we want to explore. So this is the browser main page. what you see at a glance is a cloud-free Sentinel-2 mosaic of the globe. So this is already quite detailed, and you can zoom around and explore different places. This is where you set the language. We actually have quite a few languages now, but we are also welcoming contributors who are ready to translate the data space interface to new languages. This is where you select the image date. If I just click Show Latest Date, it's going to give me the latest cloud-free image. And then the tools for creating an area of interest or marking a place with a pin or measuring a distance are over here on the right side. This is where you download an image. And images can be downloaded. This basic download is just 600 by 800 pixels with captions in JPEG or PNG. This is sort of optimized for sharing on the web. Analytical download is where you can actually select the individual data bands that you want to use, or the visualized product. You can select the coordinate system, at least from a couple. We have several data formats. So if you want to work with the data, then this is probably the download that you can use. And then we also have an option for high resolution printing. This is where you select the data source. And I'll walk you through the collections in a second. And this is where you select the visualization. And there's one more thing I want to show, again, here in the very beginning. In the configurations panel, we have several configurations optimized for different use cases. So a configuration is composed of a collection of pins. So if you click on one of these, it's going to take you to a specific place and a specific image. And we have a bit of an explanation of why this is interesting. But additionally, if you just click on Show Latest Date, you will see a number of layers, visualization algorithms optimized for this particular use case, this particular theme. So if you just want to check out a couple of examples, or you're interested in one of these applications, it's a good idea to start directly with some of these data collections and pins. Now let me move over to the search interface. This is what you normally see, right? The visualize interface. But if you click on search and you zoom in on a specific area, let me go to Cape Town for now, then you can query the data by data source. You can apply really detailed filters. Here I'm working with level 2 data. I'm pulling the cloud cover down a bit. I want to, for example, I only want to look at data collected with Sentinel-2C. I have a 1 month time interval that I can set here. And if I click on search, I have to wait a bit because it's querying a month of images. But as you will see, I get a small preview for every image tile that's available within this interval. I can look at some information about the data product, and I can download it here. Now, if you want to download a large set of data, but you don't want to do it in code, then the easiest way is to add it to the workspace. And then if you go to the data workspace, it will show you a list of the data sets that you pushed here. And if you select them all, then it's also possible to download them in bulk. So this is a very simple tool to download maybe 100 images, even if you don't want to do it in code. It's a lot better to do it with the API or not to download at all. But this is a tool we like to show because it's an introductory level thing. Now coming back to the data sets that are available, I'm using the visualize panel again. Just finding the Nile Delta here. So Sentinel-2 gives you optical imagery, but this is not just true color images, but it has 13 spectral bands. So this is the spectral explorer. I clicked over here and I'm sharing the image in the chat so you can follow. If you click on share, you can generate a short URL and you can paste it to somewhere. And if you click on that link, then your users will see the very same scene. So the spectral explorer shows me the value of the individual spectral bands. This is a nice tool if I want to develop an algorithm or if I want to understand the differences between various land cover classes. I'm moving over to Sentinel-1, which is a synthetic aperture radar dataset. So this shows you vegetation structure and terrain properties and urban areas, and you can apply various visualizations, and it's not really affected by clouds or weather. And then we have Sentinel-3, which is a lower resolution satellite, but it collects data every day. So this the spatial resolution here is 300 meters, but as you will see in the Spectral Explorer, we have a lot more spectral bands, so we can understand the properties of our surface in a lot more detail. And for Sentinel-3, we also have processed level 2 products. So these are calibrated to actual physical quantities representing vegetation. OTCI is the OLCI terrestrial chlorophyll index. And we also have the FAPAR and the water vapor column. And we also have Sentinel-3 level 2 products for water. Moving on quickly to Sentinel-5P. This is the air pollution satellite. It has relatively low resolution. You will see that these pixels are several kilometers, but it also collects data every day, so it's possible to look at detailed time series. And then we have the elevation model, which is also a nice tool. And actually, it's possible to create a profile, an elevation profile of a place. Based on this model. And then we have various Copernicus products, which are already available inside the browser. Oh yes, one more dataset I have to show in the search panel. In addition to the Sentinel datasets, you will see here that we have CCM data. These are Copernicus contributing missions, so they are higher resolution datasets provided for various parts of the world. These are not available yet for direct visualization in the browser, but this is also coming soon. But you can select and download them using the search interface. One more thing for the browser. I'm going back to Sentinel. Oh yes, the mosaics. Sentinel-1 mosaics are available every month. You will see that they are a lot easier to use than the Sentinel-1 images themselves, because they are a composite of images from a longer time period. And this means that the speckle effect, which is characteristic for radar, is much reduced. And Sentinel-2 mosaics are created every quarter, every 3 months. So this is again a seamless, high quality data set with no clouds. But the only problem with it is that it only has 4 bands. So it doesn't have all the vegetation bands of Sentinel-2. The next thing I want to show you is how to work with custom scripts. So custom scripts are actually small pieces of code describing the data processing and the data visualization that happens when you load an image. So remember the API request. We are sending a request to the server to display this image that we are currently looking at. Let me zoom in a little bit more. So the true color visualization has bands 4, 3, and 2. And let me show you how this works actually in the engine room. If you click on this little code icon, and I'm opening this up, then here is the visualization script that we are using. Let me create a little bit of an easier one. The first thing when you want to work with custom scripts is this little drag and drop interface. So you can simply pull the spectral bands and drop them on the red, the green, and the blue band of your image. And then you will have a visualization. You will see that this is true color, but it's not as pretty as the true color with the long script. And then if you click on custom script here, you will see the code that you have generated in this interface. A custom script has two parts: the setup function, where you tell the machine what datasets to work with and what outputs to generate, and the evaluate pixel function. This is the actual mathematical operation that you use. We have a custom scripts repository. So this is a GitHub collection of scripts that you can use with Copernicus browser or with your API requests. Let me give you a very simple example. This is kernel NDVI. So the way this works is that you copy the script and you paste it directly into this code window. And then it runs. So what does this script do? It takes two bands, the same ones we use for NDVI. It takes the scene classification layer, which handles the clouds. It applies a color ramp. It applies a bit of a cloud classification based on the scene classification layer. And then it outputs the values that you use for visualization. So this is how you can load a custom script, or how you can experiment with your own scripts in Copernicus browser. So much for Copernicus browser. I want to show you another interesting data source. So from the CDSC main page, you can go to the Stack browser. Stack is a protocol or a standard which allows you to describe data and metadata in a standard ready way. And then using Stack, it's possible to put together API-based Earth observation pipelines and work with your data in code. As you will see in this catalog, we have quite a lot of the data products that are available in Copernicus data space ecosystem, including some long-term composites, some air pollution products. And so there's a lot of data here that you can directly access using the Stack protocol. If you're not familiar with Stack, I'll show you in a moment how to get working with it in the Jupyter lab. In the last couple of minutes of my presentation, I want to show you how to work with Jupyter. So you click on the Jupyter lab here. Go access Jupyter lab. You click the CAPTCHA, and it's going to generate a virtual machine, a small server for you, where you will have the dependencies for Jupyter already pre-installed. And there you can run the predefined tutorial notebooks. You can edit them, or you can write code of your own. While we are waiting for this to set up, I will show you the repository. So this is the notebook samples repository. This is the repo which is also linked inside the Jupyter lab itself. Here we go. Yes. So now if you click on the samples, in Sentinel Hub, here you will see a collection of tutorial notebooks. And the way this works, you will see these are the markdown cells where you can just read the descriptions. These give you the instructions of what to do, and these are the code cells, which you run by clicking on them and hitting Shift-Enter. Now for Sentinel Hub, you are not using the direct login page of CDSC. You have to generate some credentials. You have to create what's called an OAuth token. And this is something you do in the dashboard here on the CDSC main page. Let me show you once more. If you just go Analyze Data in Sentinel Hub, that takes you to the dashboard. And here in the dashboard, under user settings, you can create a new OAuth client. And this is what you will use to generate your credentials for handling a Jupyter notebook. So in addition to Sentinel Hub, we also have tutorial notebooks on Stack. This is where you will see the descriptions for how to get working with the Stack protocol. And we also have tutorial notebooks for OpenEO. I think my time is up now, so I will hand over to Pratisha and Jeroen, and then we can come back to the Q&A and discuss the applications in more detail if you have specific questions. Thank you.
Thank you, Andreas. Maybe then I can directly share my screen. Share the entire screen if that's fine. I hope you can see my screen. And I can see Andreas' head is nodding, so I assume that's fine. So, okay. Hi, everyone. Good morning. I'm Pratiksha, a remote sensing data engineer in the OpenEO team. And today I'm joined by my colleague, Jeroen, who is the OpenEO product owner. He will be supporting me throughout the presentation and also in answering the question that you may have. If we look back to the presentation that has already been discussed during this webinar series, you have already heard about the different collection that Copernicus offers and how these collections are used in different projects to produce valuable products. So in this session, we try to answer the question on how to use those collections to produce similar application for your use case. And a simple answer to that would be using OpenEO API, which is one of the streamlined data access API offered in the Copernicus data space ecosystem, which was already mentioned by Andreas. So my presentation would focus more on introducing you to what exactly is OpenEO and how you can use it. I will try to show that with a series of demonstration where we will access the dataset from Copernicus data space ecosystem backend and also reuse a couple of algorithms that is already prepared from this data set so that everyone can use, and we will try to use one of those. But before jumping into the code topic, let's take a step back and reflect on how these remote sensing data sets are valuable. We have already discussed on how this data set can be useful in making informed decision based on several products that are prepared with this satellite data, whether it be using for land monitoring purpose, for ocean monitoring, air quality, urbanization, or many more. However, there lies series of challenges when trying to address these products or trying to work with the algorithm to generate these products. Especially the challenge lies in handling large volume of data set. They could be available in different platforms, they could be available in different formats. And once you figure out all those information, all those questions on, okay, I do have to deal with this much amount of data set, they are available in this location, and my algorithm is ready, then the question comes for how to make my algorithm more scalable and reproducible. That is what OpenEO has proven to be useful. And with that, having said that, I think I can already bring in some of the use case that was also shown in yesterday's presentation that have successfully used OpenEO, and we can already see the result is quite nice from it. One of those was ESA World Serial. So in ESA World Serial, the challenge lied in acquiring large volume of data set. And also there was a challenge on how to enable users to bring their own data set or their own model. And this was addressed when the algorithm or the workflow was developed with OpenEO. So now with the algorithm has OpenEO component in it, and it can directly access the data set from the CDAC backend. And also there are services implemented which can be used, which can be reused by the scientific community by bringing their own area of interest where they want to calculate the crop plan or the cropland maps. For that area of interest, a time series data set will be calculated, further on which classification will take place. So that is one of the use case where it has been addressed using OpenU. The another use case that also Ruben mentioned yesterday in the presentation was regarding LCFM. So in LCFM, the challenge lied in how to make the workflow more scalable, as the LCFM has to produce yearly continental products and finally use these products to prepare a global land cover map. The aim was also to provide with a dynamic service so that it can be used by a wide range of audience to prepare their own land cover maps. And to the right, you can see the product that is generated with the workflow that uses OpenU. It is annual median composite of Sentinel-1. And the whole workflow took completely in cloud-based infrastructure that was also highlighted by Andreas earlier. So this is another example of how OpenU has been successfully implemented in one of the well-known or one of the useful remote sensing application projects. Similar to that, we also have another project, which is EU Africa Luisa, where they focus on providing with a net primary production product, and they want to provide it on a yearly basis or for yearly products at 1 kilometer resolution. The challenge here was similar to LCFM to make it more scalable, as it had to be done in a continental level. And as you can see to the right, there is a map that was produced using the OpenU-based workflow for entire continent of Africa. It is for 2019. And to generate this product, it was a single OpenU batch job or single OpenU job that ran in the cloud for almost 25 hours. We are very proud with this result, so we really like to show them how it is useful or how it has been proven to be helpful to derive such products. These were few use cases. Having said that, I would like to highlight on the fact that most of the application that we have in Vito uses OpenU to get the final result that is required in the project. Along with that, we also support different external clients who want to develop their workflow in OpenU. But yeah, this was just few examples that I wanted to highlight here. But yeah, there are couple of other resources as well. So let's now move to a next question of this presentation, which is what is OpenU or how to use it. So for that, maybe I can start with a simple definition of OpenU itself. OpenU is a standardized interface or API that focus on simplifying and unifying the Earth observation data processing and analysis. So as you can see in the image, with OpenU as a single interface, we try to simplify it for user to access data set from different backends or to connect to different backends using the same algorithm or the same workflow and produce useful results. So the OpenU instance in Copernicus data space ecosystem is actually the primary product for streamlined data access to all the Copernicus products. The information that I wanted to depict in this slide has also been mentioned by Andreas. If you remember, there was a slide on download versus API. So that is similar information that I want to say it here, but maybe it would be relatable when I try to show how I used to do actually. So when I wanted to create a remote sensing application or when I wanted to perform some analysis on remote sensing data set, I used to run into different platforms to see whether they have data set available there or no. And if they had data set available, I will sit down in front of computer, as Andrea said, and wait hours and hours to download the entire data set. And once I download, then I had a series of pre-processing steps to do because, yeah, I just wanted a small clip of the data set, not the entire data set, but I had to download. So I downloaded the entire thing. Once it is ready, then only I can move towards the core part that I wanted to focus, which was to apply algorithm. I managed to download the data set. I have algorithm ready, which might be working well, but I wanted to do it on a large scale. So I downloaded a lot of data set. And now it leaves me with the challenge to also learn about high performance computing, to learn how can I parallelize the data set. So this was a long, tedious process before I finally get the output that I want. And still I'm left with the challenge on how can I efficiently share it among the scientific community. This is a traditional way of working with a remote sensing dataset, and yeah, it is nice way, but do we want to continue with it if there is a solution that's proposed out there which makes life easy or which makes the workflow easy? Then I think it would be nice to shift to the OpenU, because with OpenU, you can directly access, you can use the same uniform method to access wide range of data set. There are series of built-in process that's already available in OpenU. A simple example that I can give you is there is a process of NDVI. So you just get the data set, you call the data set for only your area of interest. You just say, get the NDVI for me. Then it gives you the NDVI. But yeah, if you have some algorithm where you want to calculate NDVI in completely different way, and you want to integrate your own algorithm, then that's also possible through custom process, which is known as user-defined function in OpenU that it allows. And finally, I don't have to worry anymore on handling the data set, on how large the data set is, or how does the parallelization works on backend. OpenU handles it for me. The final result that I get is follows the stack standard, so you can easily share it among the scientific community, and not just the data set. The algorithm that I develop is standardized, so you can share it among different platforms, reuse it, and also reproduce the result that was developed using the algorithm. So that is why we propose to use OpenU, and it has always been helpful in those applications. So diving a bit deep in how actually OpenU works. So in OpenU, it takes this data as the concept of data cube. So data cube are basically multi-dimensional arrays with one or more temporal dimension. The idea of including it as a data cube was to make it easier for users so that user need not deal with the file formats, data loading, or memory management related issue. So when these data cubes are linked together with different processes that you have in OpenU, for example, the built-in process that I mentioned, as in this example in the figure below, you can see there is Sentinel-2 data set on which a process, which is called reduced dimension, has been applied. So when these are linked together, you get a workflow which is known as process graph. Process graph as simply JSON representation of the whole workflow that can be reused in different platforms. But you can build this whole algorithm in any programming language, whether it be R, Python, whichever you preferred in your preferred environment. And everything of this happens in cloud. So far, you don't have to download anything to perform analysis on this data set. If you want to learn more about DataCube, the different process that can be applied and how are this process applied, I would like to invite you to a MOOC that is publicly available for free in the EO College. It is called Cubes and Clouds. So please feel free to visit that MOOC and learn more about the DataCube. Having said that, one of the important topics that often come across is to highlight the fact that OpenU is a free service that Copernicus has to offer. But for fair usage of resources, each user who are registered in the Copernicus dataspace ecosystem are currently provided with 1,000 credits per month. So these credits are replenished each month. You will get 1,000 next month if you finish the credit within this month. No need to worry on that. And for the question on what can I do with this 1,000 credit, to give you a simple example, maybe, creating cropland map that has been offered from the World Serial algorithm. So you can run 250 World Serial jobs or World Serial this algorithm for approximately 250 kilometers square. So a single job will be 250 kilometers square, and with that you can run 250 of them. Credits that are consumed while running this job are typically for cloud uses that it consumes. So larger project will definitely acquire extra credit, but we are very transparent in the fact that we provide the users metrics after completion of each job. So once your workflow is completed, you will get this users metrics that will give you an idea of how much CPU usage was done or memory usage that accordingly leads to the credit cost. Having said that, please be aware with this, or please keep in mind this fact that OpenIO is a service provided by Copernicus for free, and the algorithm that you want to share, for example, you develop everything. In this case, in the example that I recently gave, World Serial example, where they want to share their algorithm, these are simple and free process. You can register it in different platform for free. You don't have to, you are not charged with any credits or anything for sharing those algorithms. I will also try to highlight that during my demonstration part on how algorithms are shared. So having said that, let's move to with OpenIO now. What are the advantages? So these are actually the aim or the objective that we always highlight while introducing you with OpenIO. So with OpenIO, now you have uniform access to multiple data sets that are available across different backends. The workflow that are developed are scalable and efficient, and you can use any programming language across different platforms. You don't have to worry about the underlying technology and software while developing this algorithm. And a strong message that comes from an open source community, as we are part of open source community, is we support the principle of fair data and open science. So the workflow are reproducible and transparent, and that are developed using OpenIO. To get started with how to use OpenIO or where to use OpenIO, if you want to use in a programmatic approach, you can use your preferred code editor. In this example, I'm just showing you a screenshot of Jupyter Lab environment from the ecosystem that was also mentioned by Andreas. So you can use there. We have Python kernel as well as R kernel available over there. Secondly, we also have OpenIO Web Editor, where you can simply drag and drop the collection that you want to use, drag and drop the process that you want to connect, and create a workflow to run in the cloud. Another platform that we also have is the OpenIO Algorithm Plaza. So this is the platform where you share the algorithm and is used by the scientific community. This is the standard way of how OpenIO workflow would basically look like. I will also show you, or I will explain you during the demonstration part in a notebook. But I think it would be nice if we remember this step, or yeah, I will try to go in this flow, because this is generally what happens in an OpenIO workflow. We try to authenticate or connect to the backend where we want to access the data set or want to process. We load the collections from different endpoints, and then there are a bunch of built-in process as well as user-defined process that are included in developing an algorithm part. And there comes the final step where we write down the results. So I think it would be interesting if I show you directly in the demonstration how it looks like, or how does this workflow basically is. So for that, let's start from the data space ecosystem website itself. And it is similar step to what Andrea showed. Just go to the Jupyter Lab environment, access Jupyter. And for me, it was already open, but never mind. So this opens the Jupyter Lab environment, and you have your own folder where you share the results, and there's samples where you have a bunch of examples provided. When you go inside OpenIO there, if you are using this for the first time, or if you are using OpenIO for the first time, then I would recommend going inside the OpenIO introduction part, where everything that I discussed today in the presentation is also available here on different definition of OpenIO, how OpenIO works, what are the added value with OpenIO, how to get started, an example of analyzing heat wave in the Netherlands using OpenIO Python client, and different step-by-step process. But in this case, I think I will go with a simple example of just trying to get the collection. So I go back to the OpenU folder and take any one of the example. So let's try to run. So let's not focus on the definition of what this notebook does. But for the first step, as I mentioned earlier, let's authenticate. And in this case, I'm trying to connect to the OpenU data space ecosystem backend. So from there, I will try to get to the different collection that is offered in the ecosystem, and I will run the workflow in this backend. So I connected, and if this was your first time, then you will get a link where when you click, then it will lead you to authentication page of CDAC. And in the next step, I'm just calling the collection that I want to use. And from Sentinel-2, I'm just loading the RGB band for a month period for this extent. And the maximum cloud cover that I want is 50%. So when I click on this, how my cube looks like is this one. So the data cube is ready. That has different bands, special extent as I defined, and temporal extent. To reflect back to the process graph that I was saying, this is how it would look like. I just did cube flat graph, and this is how it comes. If you just don't do this, this is simple data cube that you see. And the flat graph, the process graph shows what is happening within this thing. In the next step, I'm making use of the OpenU process reduced dimension. But before that, let's see what actually this reduced dimension do. So I'm taking the connection that's here from OpenU CDAC backend, explain the process or describe the process. That is reduce dimension. So it gives me the definition of what actually this process does. So it basically applies a reducer to the data cube that I created by collapsing all the values in the given dimension. So in this example, I'm just saying go to the time dimension, collapse everything based on max reducer, and get me the final result. So now this is how my data cube is looking like. And if I click here, you will see the maximum data is done. And accordingly, it takes the input from there. You can interact with what is going on and everything like that, just visualizing. Now, next step, as I said, that was making use of built-in process that OpenU offers. But for example, we don't already have the process in OpenU that would meet your requirement. In that case, you might want to bring your own algorithm. So that is where user-defined function concept comes. And in this example, I'm just preparing a rescaling-based workflow. So I just get the data set from my cube, I rescale it, and send it back. That's the simple example that is done here, but it can be very complex as well. And you don't have to, or it's your choice. If you want to put it in the inline string, that's fine. Otherwise, it can be in a separate Python file like this. And in there, you can write it as you used to write your standard Python workflow. So if I do this, and I apply the UDF or the user-defined process that I did to my data cube, and if I again look at the result, then this is how it looks like now. I took Sentinel-2, applied reduced dimension process from OpenU, and I again applied the user-defined function that I defined to rescale. If I go a bit deep, then you will already see what is there in this workflow. So my workflow is ready. I have my RGB that I am interested in, so I just want to download this. And I just hit the cube download. So in case of OpenU, we have two ways to get the final result. Either doing synchronous job-based method, which is simply downloading the result. And this is recommended to use when you are working with very small area or small time frame. However, if your workflow is very complex or your algorithm does a lot of things and you are trying to execute in a larger area, then it is recommended to use something called batch job. I will show you later how the batch job looks like. So as you can see, it just ran in 2 minutes, and now I have my result here. And if I visualize using basic Python functions or basic Python process, this is the RGB only for the area of interest that I wanted to do. So that is a simple workflow of getting the Copernicus data set, applying rescale algorithm on it, and getting the final result. Now let's move to advanced cases where I want to do more, or I want to use a complex workflow. So for that one, I would go back to the ecosystem website so that it's easier for you to navigate. Let's go even further. So here, if I before executing the complex algorithm myself, maybe it would be nice to show the algorithm that is already prepared by someone else. So for that one, I go to OpenU, and in OpenU, there is something called Share Your Own Work on the Algorithm Plaza. So if you click on this, you will see there are a bunch of workflows that are available there, such as this biophysical parameters that describe that what was done in this biophysical parameter, what was the methodology used, and now how users can simply use this. A similar example would be from World Serial. So now users can provide their area of extent, as I mentioned earlier, to create cropland map. So for this, if I just click on Get Started, this will lead you to the example case. So if I go back to my notebook, create a new notebook, say this, then you can see there is a bunch of steps that's involved as we discussed earlier. So you just get the authentication, and once it's connected, you define your parameters. So in this case, it's the area special extent and the temporal extent. Okay, I think I did something. Oh, okay. There is something that I typed by mistake, and there is space that should not be there. So you define your special extent and temporal extent, and simply call the process that is there. Let's just skip this part. And if you see here, I'm calling the process World Serial. And if I see what is inside this is a simple JSON file. And what does this JSON file include? Okay, it is a process graph that includes all the workflow that is happening in the World Serial, which might be very complicated for me, and I don't want to run everything of what World Serial did, but I simply want to get only the cropland map. In that case, I can simply use the workflow that they shared as a JSON file for the temporal extent that I'm interested in, which was for 2018, and the special extent. And if you remember, the final step to save the result in which final the workflow happens, in previous case, it was download. That was a synchronous approach. Now this is a batch job-based method. And I think I did something again. Okay, yes. So while copying the things, I just messed up. So as you can see, it starts. So let's see where we can find this information. So this is running, but while it's running, let's go back to this website. And here, when you click on OpenU itself, it leads you to the endpoint. This is the same endpoint that we used in the notebook to connect to this backend where the processing will happen. So that's the same endpoint. And when I log in with the authentication of my Copernicus data space ecosystem, it lands me to the web editor, OpenU web editor, where it will show the bunch of other workflows. So that was, and you can see something is running already. My World Serial job is running. It is queued. So I didn't have to worry about parallelization. I didn't have to worry about what was the extent, what are the data set available, and all those things. So that is how you can do programmatic approach. But for example, you just want to draw a bounding box. You don't want to run this whole thing. You don't want to go to the Jupyter environment. So in that case, I would advise you to go to the World Serial repository, World Serial website. In there is something called Explore, and there is Processing Hub. When you click on the Processing Hub, it asks you again to log in with the Copernicus Dataspace Ecosystem endpoint. And in there, you can generate custom products. It's something similar what we did in a programmatic approach, but in a graphical user interface. So I want cropland map with default model at this point, and I want to set the parameters. So if I go somewhere here, maybe, and I say, okay, calculate me cropland map for this whole area of extent. And the ending month should be December, and I just want it in GeoTIFF. So it gives me what is my extent that I'm requesting for, and it was only 5 kilometers square. But if you go a bit below, then you can see how much credits are required to run the job. So 250 kilometers square is something, it's mentioned here, that asks you with 40 credits, and I'm just running it very small. So I can run it. It's not a problem to run it for a small, but what I wanted to show is you can go as big as you want in this case. So I just clear and clear the drawing, stop drawing, clear it, and I go a bit into, okay, sorry, zoom out. So that was something that I wanted to do, but it was, yeah. So I just did a larger square. So now it is 500 kilometers, and I still need not worry. I just say create job for me. So when it creates job, you can again see this, that there is a process of start the job. So you can also find the same information here. As you can see, something else is running for me now. And if I go back to the website, then it was mentioned in the previous step, which I forgot to show you, that it will take 50 minutes to run for 500 or more square kilometers. So I didn't want it to wait for that long. And that's why I already did some job in the morning. So when I click on this one, I get the same information. It is World Serial process, and I saved it in GeoTIFF. And if I go for programmatic one, then it's same. It's just the difference in date. It's saving the result. So it is already running for me. I leave it for running. And if I look at the information on the job that was finished, here you can find what was the ID of the job. That might be required when you face a issue or error and you would like us to look into it, then we would be requesting you for this ID. Then the total credit that was consumed in this job is 129, because if I go back to World Serial and I see the process that I ran a couple of days ago, then it was for a slightly larger area. And this is the usage metrics that I showed you earlier, based on which the credits are calculated and deducted from your account. Here you see the process graph. This is in a graphical view. This is a simple JSON representation. And if you go a bit below, then this is the area where I processed it. And if I go a bit further down, that I can see the data set that was used while processing the service. So for example, in this case, when I want to download this, if I was doing it outside OpenEO on my own, then I can imagine how much data I had to sit down and download. And it was not a single kind of data set. They use Copernicus DIM, they use Sentinel-1, and they Sentinel-2. This was the amount of data set that was used while creating simple product. And it just took me an hour to complete the whole thing. And now all I have to do is download the data. I only had to worry about the 120 credit out of 10,000 credits that was used. And once the data is downloaded, or I can also directly visualize it here. But since, I'm running a lot of things in here, I think it's taking time. And I downloaded the result already to show you. And this is how the product looks like. So it provided me with 2 bands. And I use the classification band which classified whether it is cropland or it is not cropland. And based on that, this is the result I get. I'm not an expert of the world serial, what's happening. However, the result looks nice to me because it is able to identify for the road it is saying it's not, and I assume this is the cropland area. So it has been able to classify it properly. And this was done in a very easy manner. So, okay, it seems like the data downloaded. So it's something similar you can explore here. I don't know. That is 0 to 1 is the same output you get. And the probability array is the other band that you get as a result of this. While this is running and the other is queued, so it will identify on its own when it is when the resource is available and then accordingly run for me. I need not worry, it will complete and download the result for me. So that was how you can already use the workflow that is prepared by someone else. And for the complex example that you might want to use, I have in this, I think this resources will be shared with you. So I already shared a couple of examples that could already be useful for you. Though I also mentioned OpenEO community example repository, which would provide you with different examples that we from the OpenEO team try to provide to all the users. This could be one of the interesting notebook for you, where we do dynamic land cover mapping using simple random forest based method. So it gives you a, so in this example, as you can see, this was random forest based prediction for entire Belgium. So what it does is explained all in here, followed by how it connects to the backend, the pre-processing step of loading the data set, masking out the cloud, and calculating different indices that will be used as a feature to the model, and accordingly create it is Sentinel-1, Sentinel-2, combining both of them, and then using the random forest based or the machine learning implementation that we have in OpenEO, one of the support that's provided. You can just run this. As a result, you will get a model which can be shared within the scientific community or within your team alone itself. Based on this, final prediction is done. So this notebook could be of interest to you. Similarly, we have a couple of other notebooks such as partial delineation, which uses Sentinel-2 data to perform partial delineation based on the model that was already trained. There's also example on how to use ONNX models in OpenEO, and also an example notebook that shows on how to handle large-scale jobs or how to distribute the large-scale jobs for your workflow. This could already be interesting. And if I remember well, then there was a question regarding the different data set or the harmonized data set that is available in some other platform that you would also like to use in your workflow. So in OpenEO, yes, that's possible that you can access the data set from a different endpoint or from a different provider. And if the data set is already available as stack, then you can simply use the load stack process of OpenEO. And in this case, this is one of the example where we have used the harmonized biomass product from some other provider. So the Planetary Computer provided us with a stack, and here we have used the harmonized biomass collection, on top of which I'm also loading the collection, DEM collection that is already provided from CDSC, and based on that, I'm merging the data set and doing further analysis. So these are couple of resources that I believe would be useful for you. And there is also the link to the OpenEO Algorithm Plaza, where you can already start using the algorithms that are prepared by team. And you can also share your own algorithms in the Algorithm Plaza. It is growing. So yeah, it is growing. So you can provide your own, or you can always come back to the platform to see what are the new services that is recently offered in there. With regards to this community support, as I mentioned earlier, OpenEO is an open source solution. So we support the open source community, as well as we provide a bunch of services or support within the community. Having said that, we also request you to collaborate with us in providing this support. But if these resources were not sufficient or did not answer your question well, then please feel free to post your question in the forum. We will try to answer them as soon as possible. We have our team dedicated in answering this as soon as possible to address your questions. Having said that, I would like to conclude my presentation with these notes on how OpenEO API is helpful in accessing dataset from multiple platforms, how it provides a simple representation that is useful in different backends. It supports multiple programming languages and is independent of underlying technologies. With the workflow that is developed in OpenEO, you can process petabytes of data without managing the infrastructure by simply using cloud-native backend. And the workflow would be reusable. So write once and run many times, and also share it. I think that's one of the core messages that we would like to share. As a remote sensing data analysis, so I think I will also like to raise this discussion or spark this discussion on, do we want to continue downloading the data set to perform analysis, or try this efficient solution that is proposed using OpenEO for data analysis in a cloud-based environment? With that, I would like to conclude my presentation. Thank you everyone for your attention. And I think now we can move to the question answer session. So for that, maybe I can stop the slide. And yeah, we have Yurin as well.
Yeah, thank you, Pratisha. I think you can see the Q&A if you, also Andras, you can come on screen because there are questions also for you, I think. Okay, let's go to the first Q&A, to the first question in the Q&A. When accessing the products like land cover maps, can we also get information about accuracy of the products?
It depends on the product. Some of them publish also the accuracy as a separate band, and then indeed you can access it. So the processing systems just give you all the information that, of course, the providers create. If they do not create an accuracy band, then of course it is not there. But yeah, many of the high quality products do have something like that. And in certain cases, you can even go back to validate input products and so on. So this is a quite positive movement that you can do more and more in terms of investigating where it came from, especially if it was created with OpenEO, where you have the full lineage, even sometimes of the workflow that generated the data.
Thank you, Jeroen. During your presentation, Andras, there was a general question if you can explain the difference with the Google Earth Engine, because a lot of the participants are using actually Google Earth Engine and they would like to understand the differences, the advantages, etc.
The most important advantage, I think, is that Google Earth Engine, I haven't used Google Earth Engine extensively, but as far as I know, it gives you a set of processes that you can run, analysis processes, algorithm creating processes, raster math, even machine learning, but definitely a fixed set. And CDSC goes beyond this because you have options to really build your own code sort of outside of the originally provided functions. And OpenEO is the most powerful with this, because there you can really create a user-defined function. You can take some Python code that you generate yourself, and by defining it as a user-defined function, you're connecting it to the database. It runs with the API on the imagery, and it outputs the end product. So this means it's a lot more flexible. The other big difference, of course, is that CDSC is a public infrastructure. It's governed by a public service level agreement, and it doesn't collect any sort of personal information other than the amount of quota that you use. So while with Google Earth Engine, I haven't reviewed the terms and conditions exactly, but I think that you actually allow Google to work with your code or to have access to the code that you develop. Well, this is definitely not the case in CDSC. Everything you develop is owned by you. We do not form any claims to your code. And additionally, there are some data products which are only available in CDSC and not in Google Earth Engine. So Sentinel-2 quarterly mosaics, Sentinel-1 monthly mosaics, a lot of the Copernicus products, which are also coming, are not part of the data portfolio of Google Earth Engine, but they are available in CDSC.
Okay, thank you very much. And there is another question from Edward. How can we use the ground verified data to inject back into the model to refine accuracy of the land use products?
That is also something that is now happening more and more. That this used to be entirely impossible, to be clear, with older approaches. But now, for instance, the world serial that was demonstrated, they allow you to fine-tune models based on your own reference data. And if you go to the world serial website, they have webinar videos that actually talk about this. And the key thing is that they use this OpenEO processing system, and that allows this dynamic aspect of generating the training data, then retraining the model, and running the inference. And actually, for more like the land cover team, the new land cover and forest monitoring project is also generating a lot of the intermediate Sentinel-2 composites that you need to do the land cover analysis. So also there, I think in the future, they are going to move more towards these systems. So for dynamic user-tailored land cover maps, that is really the future where we're heading with these systems. Instead of creating static maps that are not always good for a certain region, because they are the land cover maps, they train like a single model for the entire globe or a limited set of models, and that can never be as accurate, of course, as locally trained models with your own reference data sometimes.
Very clear. So there is Cynthia asking if we can share the DataCube mock course link. Maybe if you can put it in the chat for everyone to see. And I don't see any other question. If someone would like actually to intervene online, you can actually raise your hand and we can give you the floor. In the meantime, we have another question into the Q&A section from Rodney. I've been using Open DataCube for custom workflows, such as urban heat analysis. How does OpenEO scale this?
I'm wondering, what the question really is, like performance-wise or comparing it to Open DataCube.
Rodney can specify into the chat.
Yeah, it's in short, I can say it's somewhat similar. I'm not an expert on Open DataCube, to be clear. It has similar properties, I believe. So that is clear. Open DataCube is used a lot in the Pangeo ecosystem, where you set up your own system based on the Python ecosystem, so using open source libraries. So it's not technology independent. That's of course a big difference, and you have to be more tech savvy, have more Python skills to get things done. Although it's still a nice system as well. Yeah, those are some small differences.
Okay, Rodney clarified in the chat, he meant performance-wise and access to data.
Yeah. So what we do a lot, with the OpenEO on CDSE, the backend is really tuned towards the data sets and the infrastructure where we run. And so sometimes if you get open source packages, of course, it's just software. They have not yet been tuned with specific parameters. And that's where we see we have to invest a lot of time in it to make it work very well with that specific cloud environment. And that is, of course, then something that you have to do yourself. Depending on the use case, this can be easy or not easy. At least we know from our experience that offering these 70 collections or so that we have, that it's a considerable effort to really get that right and also to get the scaling right. But that's of course talking about a very big system. Sometimes if your use case is very focused on a relatively small problem, then you can get away with it. But we should be certainly equivalent or better.
There is another question related to agriculture. We have talked about the use of Sentinel's data during these 3 days, not only today, but maybe you can develop a bit more on how Sentinel data can be used for farmers in agriculture and to determine the current land use.
I think I can start and then Prateecha and Jeroen can join in. Let me share my screen again. Determining your current land use is not the typical application since normally the farmer knows what land their own land use. But do you share my screen or do you see my screen?
Yes.
But knowing the differences within the parcel are already quite interesting. So what we see here, this is a place in South Africa where we have center pivot irrigation. The farmer obviously knows the crop they are producing on a specific place. But even just a very simple individual Sentinel-2 image shows that there are considerable differences in productivity within the parcel. So you see a lot of these remnant lines and differences, and you will probably want to adjust your fertilization rate and ideally also your crop planting density to these different parts of the parcel because they have different capacity for producing your crop. And then the next most popular index, this is the moisture index. So this tells you about the amount of water in your vegetation. Of course, it's going to be low if your parcel is already harvested, and it's going to be high if your parcel is currently actively growing something, and then it will also be influenced strongly by the current water content of your crops. So this helps you decide how much to irrigate and when and where to irrigate, but also when to harvest. A lot of the crops, especially grains, are harvested optimally at a low water content. So you wait for the crop to dry and then you harvest it. And if you harvest too early, then your crop is going to contain too much water and you will have to pay for somebody to dry it. And if you harvest too late, then it's going to be too dry and the seeds are already going to start falling out. So actually deciding which is the field I'm going to first send my harvester to, that's already an application that can benefit strongly from moisture index. And then there's many different kinds of crop stress which have their own spectral signatures, stress from lack of nutrients or stress from the lack of water. And these can be observed using various spectral indices. But of course, the most important one, and the NDVI is still a highly popular index. This is the one that influences crop yield and crop vigor or crop health. So this is again an index which helps the farmer understand how well the crops are doing on his or her farm. Actually, the operational way to work with this, I think, for smallholder farmers is just to check the images every week or two to see how the field is progressing. Just like you go out in the field and you take a look at your crops, you also take a look with the satellite, you compare the two sources of information, and then you're a bit better informed, in a nutshell.
Thank you, Andras. And since you're sharing, maybe you can also share with participants where they can find video materials and trainings on the CDSC. And there is also a related question. Valentine is asking if there is a possibility to get a customized training on the OpenEO APIs for Copernicus data access and processing.
Yes, so please take a look here. We have a YouTube channel. Copernicus Data Space Ecosystem is the name. And this includes webinars on many different applications. It also includes online courses with several different items or several different videos explaining OpenEO, Sentinel Hub, introductory videos to the very basics like Copernicus browser or API requests. So in this channel, we have tutorials which guide you along specific notebooks, and I think this is a really nice starting point in combination with the Jupyter Lab and the Jupyter notebooks. For customized trainings, actually, it depends on the setting, because if you are preparing a training course with, I don't know, 50 or 100 attendants, it might be possible to organize one of the CDSE communication team to go there and do the training in person. We also do online webinars like this. It really depends on the number of the audience and the application. Because, I mean, we try to do as many workshops as we can, but of course, there's always a bit of a balance between the amount of time and energy we invest and the impact we can make. But in general, we are interested.
In this case, they can contact directly the support. They can, of course, contact the USpace support office, and we will liaise with them. But I think also the support directly on the CDSE website, right?
Maybe one more advertisement we can actually make. There are a couple of conferences coming up, Living Planet Symposium and Big Data from Space in autumn. And as sort of side events to these conferences, we are actually also delivering tutorials and workshops on these tools. So if you come to the conference, it's worth joining these tutorials. And also you can have a look, yes, to the CDSE website, the event section, and also on the Copernicus website. So we have an event sections in which we publicize this kind of events that might be interesting for you. And we have another question from Rodney. Looking back to the first day, how can new space entrepreneurs contribute in terms of developing workflows? Well, if you are working with a custom data set, it's possible to upload it into an S3 bucket on CrowdIAS and then share it using the to bring your own cog API. So you can create a collection and then ingest the data set directly on CDSE and share it as a custom data set, as a custom configuration. There's one more thing I want to show you here, which is again on the main page. If you go to the Sentinel Hub dashboard, here's a utility for collections. So this is where you would share a custom collection with somebody. It's possible to create a collection. It's possible to share it with specific users, and then they would also be able to access these data sets in the browser and look at it with the CDSE APIs. But I'm sure there's also a parallel solution somehow with OpenEO, right?
Yes. If you are referring to the sharing your algorithms or workflow, then I think it would be similar to sharing in OpenEO Algorithm Plaza, which is not only meant for these big projects, but yeah, if you also have very small projects or application that you want to share it with the scientific community, then you can share it in the same way as it is done for World Serial, which is simply sharing your stack, which is simply sharing your JSON workflow. Or another way is, yes, publishing it as a service, then you will get a namespace that you can share. That is also there somewhere in documentation. I think I will quickly paste it in the chat, but that's possible to share the algorithm as well.
One more thing to add, if you share the data set from some data source in a stack compatible way, then that means that OpenEO can directly access it and, for example, compare it with Sentinel or ingest it.
Yes, that's also possible. And it is something similar to the notebook example that I was referring to, how to load stack. So all the output that you get from OpenEO are stack based on stack standards. So they can be easily loaded back into OpenEO or shared as a stack and loaded as load stack process.
Yeah, so there is a raised hand, so I think we can take one last questions before the concluding remarks. So Xavier, you should be able to unmute yourself.
Sonia, can I speak?
Yes, please.
Thank you. My name is Joseph Morage. I am the project manager, GMS and Africa, working with Grace and other colleagues. I am so grateful to all of you, facilitators for Copernicus and data, focusing on land degradation and agriculture. I have not been able to join for the last 2 days because of the internet problem. I'm away away from Nairobi. I have traveled for another conference, but today it was possible for me to join. And therefore, I want to acknowledge my appreciation for all that you have done for us. We really appreciate. I want to request that if it is possible, we arrange another one soon, because we have seen it will help us a lot, and especially our stakeholders and other participants. And therefore, my request is that consider another training, and we will be so glad. And thank you very much. And thank you for all the participants. My request is that we would like to hear after this training what you are able to do that you are not able to do before this training. And that success story, we will be able to air it on, and it will encourage us to continue working with Copernicus and European Union. Thank you very much, and have a nice day.
Thank you, Joseph, and thank you, Grace, for involving the Youth Space Support Office into this webinar series. And thank you to all the speakers with us today and in the last 2 days for participating. For the participants, Grace is sharing in the chat survey. So please fill it with your feedback so that we can see what we can improve maybe for our next webinar, and what is your feedback and how you will be able to use the Copernicus data. We are absolutely interested in your feedback and to see if this webinar was useful for you. Grace, please, if you want to conclude the webinar.
I just want to thank all the participants for joining us today and the last 2 days that we had the webinar, and also to the speakers. You've taken your time to come and share your knowledge with us, and we're very grateful. And like Murage said, we look forward to more collaborations like this, and thank you so much.